Hello, everyone. I am Mitsunori Uemura of Ritsumeikan University. Let's start the 8th week of the Advanced Topics in Robot Control. This week, I would like to introduce two advanced control methods as an example of extension of robot control introduced in this class so far. One is a periodic motion control method using stiffness optimization for high energy efficiency based on resonance. The other is a standing and stepping control with a switching rule for the high balance capability of a biped robot. Let's understand these control methods in detail, because it will help you to learn how we can extend the control methods presented so far in this class and originate a new control method. Resonance-based control deals with robots that have variable elastic elements attached to each joint as shown in this figure. The stiffness of this elastic element is assumed to be adjustable in real time. As introduced in this class, resonance-based control controls the periodic motion of the robot while optimizing the stiffness of the variable elastic element to minimize the actuator torque for such. This optimization reduces the energy consumption and improves the motion performance. Therefore, this control method contributes to energy saving of industrial robots that perform periodic tasks, such as a pick-and-place task, and to improve the motion performance of humanoid robots that generate periodic motions such as walking and running. To adjust the joint stiffness in real time, we can use the variable elastic element as seen in this movie. This mechanism has been proposed in order to make the variable stiffness element as compact and light as possible. In this mechanism, one end of the spring is attached to the end of the link and the other end is attached to the nut of the sliding screw mechanism. The nut of the sliding screw mechanism can be moved by rotating the screw with an actuator. If the nut is located far from the joint, the moment arm of the spring force with respect to the joint becomes large. The spring force then produces large torque on the joint, and the joint stiffness increases. Conversely, if the nut is located near the joint, the moment arm becomes smaller and the stiffness is reduced. When the nut is located just above the joint, the moment arm is 0 and the stiffness is 0. By using such a compact and lightweight variable stiffness mechanism and applying resonance-based control, the energy efficiency of a robot that performs various periodic motions can be improved. In order to understand the principle of resonance-based control, I would like to introduce the control law for the simplest example as shown in this figure. The control objective in resonance-based control is not only to realize CP control, but also to minimize actuator torque. The desired motion can be any periodic motion, but here we use a sine wave like this equation for simplicity. The dynamics takes into account the minus kq, which is the torque exerted by the variable stiffness element, in the motion equation of the simplest robot. K is the stiffness of the variable elastic element. Since the stiffness of this elastic element is variable, a controller can adjust K. The control law is designed as shown in this equation using the feedback of the trajectory tracking error. Unlike the normal trajectory tracking control, we don't use feed-forward torque. The stiffness of the elastic element is adjusted by this equation. This equation is based on the structure of the parameter adjustment law of adaptive control. To analyze the validity of this control method, let us recall the physical phenomenon of resonance. Therefore, first consider the dynamics when the robot is moving at the desired sine wave by substituting the desired sine wave Qd for Q in the dynamics. By moving tau in the previous equation to the left side and I bar Qd2 to the right side, and multiplying both sides by -1, we obtain the equation for the actuator torque tau. Let K opt be the stiffness that minimizes the actuator torque tau, and substitute it for K to obtain this equation. By substituting the concrete sine wave for Qd, the previous equation can be transformed into this equation. Furthermore, by combining the right-hand side with sin omega t, we get this equation. Then, when K opt is the I bar omega square, the actuator torque tau obviously has a minimum 0. This optimal stiffness K opt is the stiffness in the resonance state in physics. Therefore, in this control, the control objective is to adjust the joint stiffness to the stiffness in the resonance state. Therefore, here we analyze whether the stiffness can be optimized while controlling the motion. First, in order to prove the convergence of the motion, we put the terms representing the magnitude of trajectory tracking error related to joint angular velocity and joint angle in the Lyapunov function v. Then we add the term representing the magnitude of the error between the stiffness K and the optimal stiffness K opt to the Lyapunov function. Therefore, if we can show decrease of this Lyapunov function v, we can prove decrease of the trajectory tracking error and the error between the stiffness and the optimum stiffness. So let's differentiate the Lyapunov function v with respect to time. The detailed calculation is almost the same as that of the stability analysis of the computed torque method and adaptive control, so please refer to that for details. By substituting the dynamics to which the control is applied and the stiffness adjustment law into the above equation, we obtain this equation. Please refer to the stability analysis introduced so far for the detailed calculation. By rearranging the above equation, we get this equation. As introduced in the explanation of resonance, the content of the first parenthesis of this equation is 0. The Lyapunov V is thus shown to decrease monotonically with time. This means that both the trajectory tracking and the minimization of the actuator torque are realized. From the above, we mathematically showed that the presented control law realizes the control objective. Now, let's create a simulation with MATLAB so that we can master the resonance-based control method-based. I think that this control can be easily implemented by reusing the simulation of adaptive control. In order to confirm the stiffness optimization, let's display the transition of stiffness on a graph. So let's take some time and create a simulation. We can apply resonance-based control to a multi-joint robot by using almost the same control law as introduced so far. We can concretely write the control law like this. Stability analysis is very complicated due to the nonlinearity of robot dynamics, but we can prove that trajectory tracking and actuator torque minimization can be realized as in the previous analysis. Please refer to the paper shown in the description box for details. I would like to show the video in which resonance-based control is applied to the multi-joint robot. In this video, we are controlling a robot with two joints which have the variable stiffness mechanism introduced in the previous video. Compared to the case where we controlled this robot without using the variable stiffness mechanism, the energy efficiency was approximately 6 times better when we used the resonance-based control. This experiment therefore confirmed the effectiveness of resonance-based control. From the above, we can understand that resonance-based control is an application of the idea of adaptive control to the stiffness optimization, and we can originate the new control concept by successfully expanding existing control. Next, I would like to introduce balance control of a biped robot that achieves the high balance ability seen in this video. This control method maintains the balance of a biped robot by appropriately switching among two standing control and stepping control. The ankle standing controller, one of the two standing control, maximally recovers the balance of a biped robot with a small disturbance. Combined use of the ankle and hip standing controllers will maximally recover the balance of a biped robot with a medium disturbance. When a large disturbance acts on a biped robot, stepping control makes the biped robot take a step to recover the balance. A switching rule optimally switches these control. This control method recovers the balance and switches the controllers based on the angular momentum around the ankle. The majority of the conventional control method for a biped robot is based on the position and velocity of the center of mass, CoM, of the robot. However, since the position and velocity of the CoM do not consider the rotation around the CoM, such conventional control cannot deal with the rotation around the CoM, and in the worst case, the robot will fall. In addition, since the rotation of the robot trunk causes rotation around the CoM, we cannot actively use the rotation of the robot trunk. In contrast, the control method introduced here uses the angular momentum around the ankle and its approximated integral value. Then, This control method overcomes the problems of the control methods based on the CoM position and velocity. So, let's focus on the angular momentum around the ankle. The angular momentum vector of the robot P can be expressed by the product of the inertia matrix M and the joint angular velocity vector Q dot as in this equation. When the ankle joint is defined as the first joint as shown in this figure, the angular momentum around the ankle P1 is the first element of the angular momentum vector P. From the Lagrange motion equation of the robot, the dynamics of P1 can be expressed like this. We can rewrite and approximate this dynamics using the approximated integral value pi1 and the angle of the robot trunk qt like this, where c1 and c2 are positive constants determined by the physical parameters of the robot. The approximated angular momentum pi1 can be defined by this equation. The physical meaning of the angular momentum is the rotational momentum of the entire robot around the ankle. Therefore, since pi1 is the integrated value of p1, the physical meaning of pi1 is the posture of the entire robot around the ankle. Therefore, we have to control p1 and pi1 to prevent the robot from falling. As can be seen from the dynamics of the angular momentum p1, we have to use the actuator torque around the ankle tau1 or adjustment the truth angle qt to control p1 and pi1. Therefore, in this control, we will consider two controllers, an ankle controller that uses the ankle actuator torque tau1 and an ankle and hip controller that uses both the actuator torque tau1 and the trunk angle qt. So let us first consider the ankle control using the ankle actuator torque tau1. As you can see from the upper right figure, if the ankle actuator torque exceeds a certain range as indicated in these inequalities, the toe or heel will leave from the ground. Therefore, we should keep the ankle actuator torque tau1 in this range. Since the ankle controller mainly uses the ankle torque and does not adjust the trunk angle, this controller keeps the trunk vertical qt equals 0. The knee angle is controlled so that the trunk maintains a constant height. The output zeroing control introduced last week is used to control these trunk and knee. This allows us to control the trunk and knee angle by using the torque of the hip and knee actuators. As the ankle torque tau1, we adopt the control law that maximizes the region where P1 and Pi1 can be stabilized while limiting the ankle torque. In this control law, a control law like the PD feedback control is used. Namely, it feeds back P1 and PI1 with gains Kp and Ki as shown in this equation. These gains Kp and Ki must be set in the proper range. Applying this control law recovers the balance, i.e. P1 and PI1 converge to zero, when P1 and PI1 are in the region represented by this inequality. If P1 and PI1 are not in this region, it can be mathematically proved that any control law cannot stabilize the robot. Therefore, this controller maximizes the stable region, because it can stabilize all regions except the unstabilizable region. Recovering balance as much as possible is an essential requirement for balance control. Therefore, to maximize the stable region is a great advantage of this control method. For details on a controller that maximizes the stable region for a robot with an input limitation, refer to the paper in the description box. If the ankle torque alone cannot stabilize the robot, we can expand the stable region by adjusting the trunk angle, because we can control P1 through tau1 and Qt, as we saw in the dynamics of P1. Therefore, we design the desired trunk angle QTD as in this equation. Output zeroing control is again used to converge the actual trunk angle QT to the desired 1 QTD. We should limit the trunk angle within a certain range so that the trunk does not touch the ground or the robot itself. Therefore, when the trunk angle is properly controlled, the stability region is expanded as in this equation, where C3 is a positive constant determined from the physical parameters of the robot and the trunk angle limitation. This expanded stable region is also the entire region except the unstabilizable region. Therefore, this controller is also the optimal one that maximizes the balance ability. As you can see from this stability region inequality, the hip controller alone can restore the balance without using the ankle controller. Therefore, the hip controller can keep the balance of biped robots that do not have actuators on the ankle. Such biped robots without ankle actuators contribute weight reduction and simplification of biped robots. In addition, even if a biped robot has an actuator on its ankle, this hip controller can restore the balance even when the ankle torque cannot be fully exerted due to the effects of irregularities on the ground. If the combination of the ankle and hip controllers cannot restore the balance, the robot have to take a step to restore the balance. The stepping controller make the robot to take a steps. When the stepped foot lands and the other foot leaves from the ground, the reference of PI1 representing the robot posture around the ankle changes. The value of PI1 then changes depending on the landing position. On the contrary, if the foot lands softly, the value of P1 does not change. Therefore, the stepped foot should be landed at the position where P1 plus 1 divided by C1 times PI1 will be the farthest from the unstabilizable region. After the landing, we can use the ankle control or a combination of the ankle and hip control to restore the balance. If that value can be the farthest from the unstabilizable region, the robot will be able to optimally recover the balance even when disturbance is added. Based on the discussion so far, a switching rule that optimally switches these controllers are designed as follows. First, if P1 and PI1 are in the region that can be stabilized by the ankle controller, we use the ankle controller. Since adjusting the trunk angle requires a large actuator torque on hip joint, we use only the ankle controller, or if we can stabilize only by the ankle controller. If the ankle controller alone cannot stabilize, and P1 and PI1 are in regions where the ankle and hip controllers can stabilize, we use both the ankle and hip controllers. If the combination of the ankle and hip controllers cannot stabilize, we use the stepping controller to recover the balance. With this switching rule, we can optimally recover the balance, and prevent the robot from falling or unnecessarily switching controllers. Here, let's consider the validity of the presented balance control from the viewpoint of kinesiology. From a long time ago, human balance control has been studied through experiments. These studies have shown that humans use mainly ankle torque to restore the balance against small disturbances. Such a balance strategy is called the ankle strategy. When a medium disturbance acts on humans, humans use the ankle strategy and at the same time adjust the trunk angle to restore the balance. This balancing strategy is called the hip strategy. When a medium disturbance acts on humans, humans use the ankle strategy and at the same time adjust the trunk angle to restore the balance. When a larger disturbance acts, humans take a step to restore the balance. This strategy is called the step strategy. Let's imagine how you restore your balance when you are on a bus or train and it shakes you. When the bus or train shakes a little, you can imagine that you're using only your ankles to restore your balance while keeping your trunk posture almost unchanged. You can imagine adjusting the trunk posture to restore your balance when the shaking becomes a little bigger. If you face on greater shaking, you will take a step to restore your balance. In this way, humans are appropriately switching their balance strategies according to the magnitude of the disturbance. The control method introduced so far also uses almost the same strategy. Humans seem to maximize their balance ability to prevent falls. The presented balance control is theoretically derived to maximize the balance ability. Therefore, the presented balance control may be a theoretical explanation of human balance control. Finally, let me introduce the video of balance control that I have introduced. The yellow bar indicates the trunk of the robot and the light blue bar is the leg. In the upper right corner, P1 and PI1 are displayed as a light blue point. The pink region is the region that the ankle control can stabilize the biped robot. The red region is the region that the ankle controller alone cannot stabilize, but the combination of the ankle and hip controllers can stabilize. When a small disturbance acts on the robot rotates around the ankle, causing the light blue point to move. The light blue points stay in the pink region, and the ankle controller restores the balance. It is the same even if a small disturbance acts in the opposite direction. When a medium disturbance acts, the light blue point gets out of the pink region and into the red region. In this region, since the ankle controller alone cannot stabilize, the adjustment of the trunk angle is also used to restore the balance. When a large disturbance acts, the light blue point gets out of the all-stable regions. The stepping controller makes the robot take a step. When the foot lands, the light blue point should be farthest from the unstabilizable region. Thus the stepping controller calculates the optimal desired landing position. The optimal desired landing position is indicated by the purple point. After the foot lands at the optimal position, the ankle control restores the balance. Even if a much large disturbance acts, the balance is restored by appropriately switching stepping in the ankle control and hip control. Although I don't introduce today, we can apply this control method to control of bipedal walking. Even in this walking control, we use the angular momentum around the ankle and its approximate integral value. The robot then continues to walk stably even when disturbance acts on the robot. The balance control introduced so far is based on output zeroing control while referring to a previous study. This control especially referred to the best CoM-ZMP regulator proposed by D. Sugihara. I would like to introduce the link to the related paper in the description box, so check it out. The great progress of the presented balance control has been brought about by the use of the angular momentum around the ankle and its approximate integral value, although the conventional balance controllers have evaluated and controlled the balance of biped robots by using the position and velocity of the CoM. By combining some existing control methods and utilizing the essential structure of the controlled object in this way, we can originate new high-performance control. This concludes the explanation of balance control. Finally, I would like to introduce homework for this week. This week's homework is to create the MATLAB simulation I described this week and submit it as a report. In addition to it, let's create an additional simulation of advanced robot control that you like and make a report of it. In the report, please include the figure of the simulation model of Simulink, the program source of the robot dynamics block, the program source of the controller block, the simulation result graph, and the explanation of the simulation contents and the simulation result. In the report of the additional simulation, let's report a relationship between real applications and reported control. Please submit the created report through Manabar. That concludes this week's class. Thank you for your hard work.